If I have a question that looks like this, maybe a block, maybe it's a wagon, whatever it is, it's on a horizontal surface as much as that's not quite horizontal. Pulling at it horizontally like this, let's say with an applied force of 100 newtons. Say I got a force of friction as well. Which way would friction act on this? It's going to act against the movement. It's going to move to the right. Friction would act to the left. Let's make that force of friction 40 newtons to the left. What other forces do I have acting on this? I have normal force and gravity. And what do we know about the value of gravity versus the value of the normal force? They're going to be balanced here. They're going to be the same value here, right? That's because if it's not accelerating up or down, the net force up and down has to be what? Zero, right? Balanced forces. There's only two forces up and down, so they have to balance each other. Therefore, Fg will be equal to Fn. What if I switch this question around a little bit, though? What if I make it like this, where I've got my same object being pulled to the left with a force of friction of 40 newtons, being pulled to the right with a force of 100 newtons, but this time we're at an angle of, let's say 30 degrees. What other forces act this time? Gravity. Gravity acts downwards. Same value as it was in the last question, right? As long as it's the same mass of the object. What about the normal force, though? Yep. It's going to act upwards, but it's going to be smaller than Fg. Not necessarily half the value, right? It depends upon circumstances what value it is, but we do know that it's going to be half the value of Fg. Why is it smaller than the value of Fg in this question, but it's the same value as Fg in this question? Yep. Okay, so when we apply our force of 100 newtons at an angle of 30 degrees, we're pulling to the right, but we're also pulling upwards. We'll call this Fx, and we'll call this one Fy. When we look at this situation now, if it's not accelerating up or down, the net force vertically still has to be zero, but now we have three forces making up that net force of zero instead of two. We had gravity and the normal force. Now we have gravity, normal force, and the y component of the applied force. Combined, those three forces have to give me a net force of zero. That means in this case, the force of gravity acting downwards will be equal in magnitude to the normal force acting upwards and the y component of the applied force acting upwards. That means Fy has to be smaller, right? If we say we want to solve for Fn here, it becomes Fg minus Fy as opposed to just Fg. That make sense? Now, when I look at this question on the bottom here, okay, assuming that I have the force of friction given to me already and not a coefficient of friction, then really, when all these vertical forces cancel, I could turn this question into this, right? I could turn this question into the last question. What would I do at this stage in both cases? F net is the sum of the forces. I'd add the forces together, right? F net is equal to FF plus FA, or F net is equal to FF plus FX, the X component of that applied force, all right? If we were given a coefficient of friction as opposed to a force of friction, up here wouldn't be that hard, right? We just have to find the value of the force of friction by saying mu times Fn. What would the value of Fn be in the top one? M times G, right? Because because the normal force balanced gravity. Remember, I erased those, but gravity was downward, normal force was upwards, exact same value, opposite direction. We just plug in the value of M times G for that. But in the bottom one, if I wanted to find that force of friction, still use mu times the normal force, but this time the normal force wouldn't be M times G, right? The normal force would be the force of gravity minus the y component of the applied force. Whatever that works out to be, I'd have to plug in there for the normal force. Got it? So if the object is not accelerating up or down, the net force up and down has to be zero. But that doesn't mean that normal force will counter gravity, like it did in almost all of the questions we did up until towards the end of last week. This time, now, the normal force doesn't have to balance gravity if there's something causing it to not balance gravity. Even if the net force is zero, the normal force will sometimes be less than gravity. Is there ever a situation maybe where the normal force could be greater than gravity? Well, let's say we're a horizontal surface, not accelerating up or down. So you're not moving up or downwards. Could normal force be greater than gravity? Yeah, or pushing at a downward angle. Yeah, exactly. So if we had a situation where we had our object like this and we were pushing down on it like this, right? Sometimes when you push something, you're like I'm pushing the desk right now, we're kind of pushing down like this with a force of 100 newtons. In this case, we would say, let's say the applied force is 100 newtons. That consists of a force to the right that we call Fx and a force downward that we call Fy, right? Good. Well, we also have a force of gravity acting downwards. What would the normal force be? Well, the net force up and down is what? 0, right? Well, if we have two downward forces, the y component in gravity, the normal force would have to be bigger than gravity in order to counter those, right? The downward force, y component, the downward force of gravity combined would give me the normal force there, right? So we're not just saying the normal force is automatically smaller. I want you to understand why the normal force is smaller in that last question, but why in this case the normal force is bigger. Don't memorize this stuff. Understand this stuff so that when you get a question that's just a tiny bit different, you can deal with it. All right. This is all versus something that looks like this. Sometimes I call it my Halloween bag problems. If those last questions were my wagon problems, these are my Halloween bag problems. You're pulling on a Halloween bag or pulling on whatever with a force to the right. Doesn't matter what the value is. Pulling down this way with an F2. Pulling this way with a value of F3. And this way with a value of F4. What's the difference? We're pulling on this thing, this bag of Halloween candy or whatever it is, from all different directions. Aren't we doing the same thing here? Upward force, downward force, force at an angle. Isn't it the same thing? Yep. Perfect. Okay, perfect response. Okay, the response was, if you didn't hear it, in this case, things cancel. The y components cancel. Same deal over here. Look at what I got on the second problem right here. We had a force at 30 degrees. We had gravity. We had a normal force. All the up and downward forces canceled each other out. What were we left with? Forces on the x-axis. F net is equal to the sum of the forces. What are we left with here? Well, nothing cancels. So we're left with forces on the x-axis and forces on the y-axis. We're still going to add them together. We're still going to add forces together. But this time, we have to add them together using a vector analysis, x and y components, as opposed to just F net is equal to the sum of the forces, right? Get rid of your funny angles. Okay, get rid of your funny angles. Okay, break it into x components and y components. Turn this F2 into this. Turn this one F3 into this. Add up all the x's, add up all the y's, and then recombine them using the Pythagorean theorem in the inverse tan function. Here's a problem for you to work on for the next few minutes here. We've got a 10 kilogram object that's being pulled with 4 forces. I think it's pretty clear that we're going to have a situation here where the forces do not cancel out. If they do, hey, great. If the x component cancels out, then it becomes F net is equal to the sum of the forces. If the y component cancels out, great. F net is equal to the sum of the forces. But I think it's pretty clear here that odds are it's not going to cancel out. And if that's the case, then we're certainly going to have to do our x components and our y components and then recombine them using the Pythagorean theorem and the inverse tan function. We got 4 forces here, F1, F2, F3, F4. What do you got to notice first about this? Assuming that nothing cancels, we got funny angles, we got to deal with those. So deal with those funny angles first, and then break it up into x components and y components, then recombine it into a triangle, do the Pythagorean theorem in the inverse tan function. I want you to find the net force, and then, if you can, after you find the net force, I would like you to find the acceleration as well. All right, we have two funny angles here. One's at 30 degrees, one's at, they're both at 30 degrees actually. Let's do F2 first. Okay, F2 is 100 newtons at 30 degrees north of east. Let's draw the x component there and the y component there. Let's say cosine 30 degrees is equal to x over 100. So x ends up being equal to 86.6 newtons. We'd say sine 30 degrees equal to y over 100. So y is going to end up being equal to 50.0 newtons. I can redraw that, and I will redraw that now with a force to the right of 86.6 newtons and a force upwards of 50.0 newtons. Okay, good. Halfway there in terms of my funny angles at least. Okay, let's do my other one now. I've got 60 newtons at an angle of 30 degrees west of south. This one's a bit different. My angle is usually measured from the x-axis, not from the y-axis. This would be the y component. This would be the x component. Which side of the triangle is the x component this time? Opposite adjacent, or hypotenuse. X component is opposite this time. So we're going to say sine 30 degrees is equal to x over 60 newtons. So x is going to be equal to 30 newtons. Last time it was cosine 30. This time it's sine 30 for x, right? So pay attention in each question. Understand which side of the triangle you're dealing with, and therefore which trig function you're going to use. The y component would be, we'd say cosine 30 is equal to y over 60. So 60 cos 60 would be 52. Let's keep going though. Let's not go to two digits. 51.96. We don't want to round it to two digits yet until we get a final answer, right? 51.96 newtons. So let's box that off. And now let's replace my 60 newtons here with a force to the left of 30 and a force downward of 51. Now we get this thing, this 10 kilogram object that's being pulled in all kind of crazy directions here. That's okay. It's not very hard now. The x components, F1, the x component of F1 would be, Quinn, what would the x component of this one be? 0. What's the y component, Quinn? Good. Nick, what's the x component of this one, the green one? 86.6, good. What's the y component? You could say it's 0, sure. And then say the third one, the x component is 0, the y component is 50. I like to combine them here. Doesn't really matter though. Okay, I just make green kind of 1. Then the next one we have F3, 0 and neg 50. And then the x and y components of the fourth one, we say neg 30 and neg 51.96. We add these together. What do we get? 56.6. And what do we get for this one? 48.04. Is that right? All right. Now we got to redraw it. Make it a right angle triangle now. 56.6. 48.04. This is my resultant vector right here, and this is theta right here. And how do you find r there? Don't just add these up. Don't ever just say 48 plus 56 is equal to 100 and whatever. Don't do that. Okay? If they're on two different axes, you can't add them the old-fashioned grade 1 way. 1 plus 2 is equal to 3. It's not. Okay? If they're in two different dimensions, you've got to do. Yeah, you got to do the Pythagorean theorem. What does that work out to be when you do the Pythagorean theorem on that? 74 for r. What's the unrounded number there? 74.33? 74.23 newtons, which we're going to round here to two digits, right? 74 newtons. Why did I want the unrounded number there? I'm going to find the acceleration in a minute, and I need the force to do that, the unrounded value of force. Theta works out to be the inverse tan of 48 over 56, which is going to be, I'm going to say, around 42 degrees. 40, somewhere between 40 and 45. What is it? 40? Okay, it would be 40 degrees north of east. All right, you want to find the acceleration. One more step here. You want to find A, what do you do? Divide the net force by the mass. We're going to say 74.23 at 40 degrees over the mass of, what was it, 10 kilograms? Gives me an acceleration of 7.4 meters per second squared at 40 degrees north of east. We don't divide the 40 by 10, right? We divide the force by 10, and then the acceleration will just be in the same direction as the force was, which happens to be 40 degrees. Good? Quiz tomorrow, going to be a little bit of a surprise. You're going to get one question. It's either going to be a question like you just did, or it's going to be a question like this, where we're pulling it at an angle of 30 degrees and it moves horizontally. Okay, I want to see tomorrow not only if you can do that question, but if you can distinguish between the two questions, right? This question where the y components completely cancel and it's just an F net is equal to the sum of the forces after you find the x component. Or this question where the forces don't cancel on the y-axis and you end up having to do the Pythagorean theorem, right? So first thing you got to do tomorrow when you see that question is figure out what you got. If you're not sure what you got, find the x components and y components. And if something cancels, it's this. If something doesn't cancel, then it's this. And then do what you need to do.